Welcome to Lesson 7, which can be found in your textbook in Section 8.3. So up to this point, we've been looking at strong acids, strong bases. We then focused on weak acids. Today, we're going to focus on bases and how they relate to the acids we've been looking at the past few days. So the first thing we're going to look at is base dissociation constant Kb. So obviously when we're talking about acids, we're going to refer to Ka. If we're talking about bases, we're going to use Kb. So weak bases, so instead of before for the acid we're using Ha because it contained that hydrogen. Well, the bases, remember, they want to accept a proton, so they're not going to have that hydrogen when we write it out. So instead we're going to use B to talk about the base we're going to be reacting with water. So weak bases B react with water to form an equilibrium solution of ions. So you'll see here in this case, the base is reacting with water. It's picking up the hydrogen from the water. So in this case, water is acting as an acid, and it's donating its hydrogen to the base. So here we have Hb plus. Because it's picked up that proton, it gains a positive charge. And then we have now water has lost the hydrogen, so we develop those hydroxide ions, which we know are associated with bases. If we take that equation and we substitute it again into our Kc value, where it's products over reactants, and then we rearrange that, again, water is ignored in this case, so Kb is equal to our products over our reactants. This one here. Many compounds present in plants are actually weak bases, so the caffeine and black pepper, they are a form of weak bases. So obviously you'd set up an ice table the same way we would with the way we did for the Ka. It's exactly the same, except now we're looking at bases which are proton acceptors. What we're going to look at now is acids and their conjugated bases. So how the acids, strong acids, and bases are all related together. So if we look at this question, we already looked at this in some previous notes. We have acetic acid plus water. Acetic acid is obviously a proton donor. So this hydrogen is going to be given to the water. We end up with that hydronium ion that we see with acids. And then you have that acetate ion all by itself without that hydrogen. We can then substitute it into the Ka equation where it's products over reactants. And we end up with this equation here. So looking at it that way, we consider it an acid. However, the acetate ion, which would be this one, is the conjugated base of acetic acid. So remember on our very first lesson in chapter 8, this would be your acid, and acids always line up with conjugated bases. So the acetate ion is considered to be a conjugated base of the acetic acid. A soluble salt of the conjugated base, such as sodium acetate, so sodium could actually now link up with acetate, forms acetate ions in solution. Those acetate ions act as a base with water. So if those acetate ions are reacted with water, in this situation here, acetate is going to want to accept protons. So from the water, water will now act as an acid here, donate a hydrogen, so we get that acetic acid back, but now we're left with hydroxide ions instead of hydronium ions like above. Right, so we have hydronium ions here, and in this situation we have hydroxide ions. So at the top we're looking at an acid, and the bottom we're looking at a base. So here, this would be considered a base, and this would be its conjugated acid. Again, if we substitute that into the Kb, it's products over reactants. Remember, water is ignored in this case. And you end up with this equation right here. Interestingly enough, if you take those values and you multiply them together, like it is right here, so Ka times Kb, so the two equations I boxed in, you'll see that this cancels out with this cancels out with this, and you're left with H3O plus, which is our hydronium ions, times OH minus, which we already learned in previous lessons that represents our KW equation. So our seventh equation, remember that other lesson where we did 6 equations? The seventh one we're going to add now is KW is equal to KA times KB. So if you have KA and you need to find KB, you can use that equation to solve for it. Just a reminder what KW is, 1.0 times 10 to the negative 14. Okay, that's a constant that never changes. So you can use that to either find your Ka or Kb if one of the others is given. Just to point out in the box there, the strength of an acid and its conjugated base are inversely related. So if you have a strong base, its conjugated acid would be a weak acid. And if you have a strong acid, its conjugated base would be a weak base. And that will make more sense in a second. Okay, so keep that in mind when we start to do our practice problems. And then one just quick thing here, make sure that you do read this in your textbook to get a little bit more background on it, on what exactly a buffer solution is. They're actually resistant to changes in pH. So they have a specific pH, so say it was 3, and anything you do to it, the pH barely changes. So it contains a weak acid / conjugated base, or a weak base and a conjugated acid pair. Have a buffer capacity related to its concentration. They play an important role in biological systems, such as homeostasis. Okay, so we're going to go and do practice problems together. Okay, so looking at this one here, it's on page 407 in your textbook. It's going to be question number 34. So an aqueous solution of ammonia has a pH of 10.85. What is the concentration of that solution? So first, let's write out an equation. So ammonia is NH3. We're going to add water to that. You guys notice the trend now, right? That we always add water to the acid or the base. And if it's a base, we're going to have a proton acceptor. So it's going to accept that proton from the water. We're going to have NH4+. And then you're going to be left with those hydroxide ions, so OH-. And if we wrote our Kb equation, so Kb is equal to products over reactants, so we're going to have NH4 OH- over our product, which is NH3. The question is asking what is the concentration of the solution. So when it says that, what it's referring to is actually ammonia. So it's asking you what would be the concentration of ammonia. So we're not really given a lot of information here, except for the pH of the solution. Okay, so our goal is to find this. So before we can do that, we got to make sure that we have these 3 things here. So my Kb, I can find that by looking it up in the back of the period, or not back of your textbook. Again, you're going to turn to page 597 in your textbook, and you'll find out that the Kb for this equation is 1.8 times 10 to the negative 5. Okay, so we have our Kb. Now we need to figure out our NH4 and our OH-. So now we got to go back to those 6 equations that we had learned previously and figure out which one's going to help us get to figure out our values. So with pH, we can use that to find POH, because pH isn't going to help us when we're looking at hydroxide ions. We want to deal with POH. So remember the equation that pH plus POH, I think this was equation 5, no, it was equation 4, is equal to 14. When I say equation 4, that's from the previous note. So pH plus POH equals 14. So if we know that the pH is 10.85, we can rearrange this and put 14 minus 10.85 is equal to POH. And then you're going to subtract those two and you end up with a POH, not time, 3.15 POH. So with that POH, we can use that to find our hydroxide ions. So looking back, remember to equation, I think it was equation number 6. So in equation 6, the concentration of OH is equal to, is equal to 10 to the negative POH. So if we substitute our values in, 10 to the negative 3.15, you end up with a concentration of 7.1 times 10 to the negative 4. Okay, so now we have our OH concentration. But just like any products, right, if I was actually to finish that ICE table, our OH, because it's a 1-to-1 ratio, my OH is equal to my NH4. So no matter, the products always start at 0, the change is going to be the same because they have a 1-to-1 ratio. So I know that the concentration of the hydroxide ions that I found down here is equal to the NH4 because it's also a product. So we have all three now. So we're going to substitute those values in and rearrange it so that we can find ammonia. Sorry, ammonium. So NH4, if we rearrange that, is going to be equal to Kb times our ammonia divided by our OH. Sorry, just erase what you'd just written before. I just kind of going crazy here. We're actually looking for NH3, so I rearranged it for ammonia, but we're actually looking for ammonia. So we're going to rearrange that for NH3. Would be NH3 is equal to NH4 times our OH, and now that's going to be divided by our Kb. So now it's just a matter of substituting our values in so we can get the ammonia. So because ammonium is equal to hydroxide, I'm just going to put the same value and then put it to the square. So 7.1 times 10 to the negative 4 to the power of 2. And then on the bottom, my Kb value, which is 1.8 times 10 to the negative 5. If you put that into your calculator, you end up with the concentration of ammonia being 2.8 times 10 to the negative 2. Okay, so for this sort of question, literally you just had to take what you knew, find equations that work to get you the hydroxide ions that you're looking for, realize that the hydroxide and your ammonium are equal, and then you can substitute your values in. All right, let's move on to the next one. So this question is on page 409 in your textbook. It's question number 36. It says the Kb for ammonia NH3 is 1.8 times 10 to the negative 5. And the Kb for trimethylamine is 6.5 times 10 to the negative 5. The question is, which is the stronger acid, NH4 or trimethylamine? Okay, so we know that the Kb here is going to be 1.8 times 10 to the negative 5. And the Kb for trimethylamine is equal to 6.5 times 10 to the negative 5. So I'm just restating what was given in the question so we can start to break it down. So it's asking you which is the stronger acid. So the keyword being acid here, but KBs are given. So remember that KB is when we're dealing with bases and not with acids. So we need to look at what Ka will be and compare those in order to get your answer. So we're going to use our new equation that we learned, which is Kw is equal to Ka times Kb. So we can rearrange these equations so that we can find our Kas for each one. So we'll say this is number 1, this is 2. So for number 1, if we plug in our values to find Ka, Ka is equal to Kw divided by Kb. So our Kw is a constant, 1.0 times 10 to the negative 14, divided by our Kb, which was given, 1.8 times 10 to the negative 5. You put that into your calculator and you end up with 5.56 times 10 to the negative 10. We'll do the same for the second question. Sorry, this should be Ka. Is still equal to Kw divided by Kb. Kw is 1.0 times 10 to the negative 14. And our Kb in this case is 6.5 times 10 to the negative 5. If you put that into your calculator, you end up with 1.54 times 10 to the negative 10. So now that we have the Ka for both of them, we need to decide which is bigger out of the two. So a bigger Ka value represents a stronger acid. So obviously, this is our winner because it's a bigger number. Therefore, ammonia is a stronger acid. Sorry, so I just made a small little mistake because this is not we're looking at the base, so it's going to be the acid, which would be NH4+. So NH4+, right, which is what the question was asking, is the stronger acid due to a higher Ka value. You could also do this just by evaluation. Some key things that I had told you previously in the note. If we look at the KBs, we can figure out which one is the stronger base out of the two. So whatever has the higher KB value is the stronger base. So out of these two, This would be the stronger base, and this would be the weaker base. So weak bases always have strong conjugated acids. And strong bases will always have weak conjugated acids. So without having to do all this work, you can just look and see which one is the weaker out of the two bases would mean that it would have a stronger conjugated acid. Okay, but if that just confuses you and you don't want to have to try and memorize that, then literally just substitute it in so that you can find the Ka value. The higher the Ka value means the stronger acid. So in this case, the stronger acid would be NH4+, because it has the higher Ka value out of the two. Okay, so that's all for today's lesson.